Hi, everyone. Welcome to my lecture. It's a pleasure to be here. I give this lecture to this course. This is the third year in a row. Every year there's new stuff. As I understand it, this course is about data science applications in neuroscience. And that's kind of what I wanted to focus on, but within my field, which is the neuroscience of language. Okay. Feel free to stop me, ask any questions, share any thoughts you have or anything. There is a lot of content. I'm assuming this will take at least an hour. But we'll see. Okay. Oh, that's not a good sign. Just as a review, what you were learning in previous weeks, or what you were asked to view the YouTube video or so on, there are two concepts which I need you to know. These are like Chekhov's guns, right? They're going to be relevant later. So the first concept is a word embedding vector. What's a word embedding vector? It is a way to represent a word with a vector, right? In this example, the vector is 7 numbers long. Yeah, it's a vector of length 7. And the numbers are not just randomly generated, right? We could have generated a random vector to every word, right? We could have done that. But no, what we want to do is that these vectors, words which are close together in meaning get vectors which are close together, okay, in space, right? We can, for every two vectors, we can see how similar they are in space using the angle in between them, right? And then when we use big data, machine learning, we train these vectors on large text and so on, we can get a word embedding vector for each word, which satisfies this condition that similar words kind of get grouped together, and also distances between words or specific directions between words also represent a common thing. So this, for example, is the direction represented to move from male to female, right? So if you start at man, you end up at woman, and if you start at king, you end up at queen, something like that. Okay, so those are word embedding vectors. They're really, really cool. The second thing we need to keep in mind is language models. What's a language model? What is that, right? Today we hear LLMs, large language models, or anything. Language models are a very simple thing. Oh, that just happened. Essentially, you give an input which is some length of text. That's what it is. And you want a model to predict what will be the next word. That's basically it. But you want it to do it in a way that makes sense, that's similar to how humans produce language, okay? So the cat likes to sleep in the, you put it into a large neural network, and it has, all kinds of architectures. We can invent whatever architecture we want, but today it's very popular to do a transformer architecture and so on. But we could have done RNN architectures, LSTMs, or any of the good stuff we know from machine learning. And then it gives a probability for each next word that it has in its vocabulary to appear. So box got a high probability and zebra got a low probability because the way the sentence works, okay? Excellent. So we've reviewed these two. Keep them in mind, and now I'm going to start my presentation. We're going to go with a neuroscience of language intro, just a little bit of brief introduction. I know some of you might be taking the neuroscience of language class. We'll just do an intro for everyone, okay? I'm not assuming you know anything. And then we'll talk about NLP and neuroscience of language. So NLP is natural language processing. It's a field within computer science which deals exactly with language and text, okay? It's where the word embedding and the language models came from, okay? It's a computer science discipline. But obviously there's a lot of overlap with neuroscience of language. And at the end, I think if we'll have time, and I think we'll have time, we'll talk a little bit about the implications of large language models today about the brain, right? What does ChatGPT, can tell us about the brain, if anything at all? I think it's an interesting question we should be thinking about, especially in the year 2025. Okay? Excellent. So I'm beginning. Part 1, Introduction to Neuroscience of Language. So let me start by saying language is important. Language is very important. I believe so, at least. It's integral to humans. It's really a core part of being humans. The Steven Pinker quote, I don't know if you can see it, is that language comes so naturally to us, we're apt to forget what a strange and miraculous gift it is that we use language every day, right? It's central in society life, right? So You can't have a functioning democracy or government without language, signs, phones, the myth, the Tower of Babel story. Obviously, it's about languages and what happens when we don't have a shared language, our society falls apart. Language is distinctive in the animal kingdom. It's true that many animals have communication systems that they can communicate, but language, the way we do language with our arbitrariness of words, the fact that this is called a table, it's pretty arbitrary, and our complicated syntax, and our ability to talk about things which are very abstract or things which, hypotheticals and so on, is probably distinctive in the animal kingdom. There are probably no other animals which can do that. Language is diverse. That's also very interesting, right? There are many different languages. I could do a poll here. I'm assuming within this class, we have at least 15, 20 languages that we know. And if you don't believe me that language is important or you don't care about language, that's also okay. But I know you're here to study neuroscience, and language could be a key window to understanding the brain as a whole. So there are certain principles that we can learn from language or from the way languages represent the brain, which might tell us about other things, which are not only language. And there's a fantastic talk by Steven Pinker, which is linked here. By the way, I'll share the slides and everything if anyone wants to see it. The talk is about how language is actually a key to much larger questions in the brain. Okay, excellent. There are many levels of language research. I don't know if you ever thought about language, but it's not really similar to other things. It's not similar to vision or motor, because it has a little bit of both. And also, it has many aspects. So it has the phonology aspects, which is the sounds that make up the language, right? We all know these, how these sounds shape the way we speak and our accent and how it sounds like. It has syntax, which is these kind of rules of how we combine words together in sentences, right? And we all know, you study a different language now, your second language, and suddenly it has different rules and you're confused. Why does the adjective go after the noun and not before the noun and so on? It has semantics. Obviously, that's a core part of language, that it means something, right? We're not just blabbering. We're not making sounds. We actually mean to refer to something. And there's also a level which is called pragmatics, which is more about the non-literal use and meaning of language, right? So we can use language in social settings to tell jokes or, for many other things, or sarcastically and so on. Language is one of the few things I would argue in the brain that we have both processing or a comprehension part, right? We understand when other people do language, when we hear language, when we read, but also has a motor aspect, an output, a production part, we call it, right? We can talk ourselves and we can write ourselves, right? So it's cool. So you can study both those systems, or just processing or just production and so on. And there are also life dynamics which interest us, like the acquisition of language, right? As kids, how it happens, or the acquisition of second languages, which we do through our lifetime. There are certain disorders which you have. Dyslexia is a famous one. I'm sure, many of you know people with dyslexia or have dyslexia yourself. And aphasia. Aphasia is a specific word which means a specific deficit in language, which is usually not associated with deficit in other things, okay? And there are certain different types of aphasias, which we'll talk about a little bit, okay? And in neuroscience of language, we kind of ask where and how all of this and more happen in the brain, right? We also add the neurobiology aspect of it, okay? All right. To do that, we have to use diverse methods. I'm sure you learned about these methods in your methods courses. So we do patient studies. This isn't a patient. This is Dr. Paul Broca, who he was, I think, one of the first ones who actively went and collected patients with symptoms, right? And then this is one of his patients. This is who had a difficulty, who had an aphasia. This was a lesion in the brain that they had. Today, we do much more, awesome statistical methods where we collect a lot of patients and we see the overlap in their lesions in the brain because we can scan them and so on. We do structural neuroimaging. So we check your, gray matter thickness and stuff like that, or DTI, which is white matter imaging, right? We can do all of that and see how it's related to language. We do electrophysiology. Electrophysiology, we do a lot of EEG stuff, right? It's very simple to do an EEG. But also we do ECOG, which is when you place electrodes directly on the scalp of patients, and also in surgery. So we do stimulation during surgery, and then we can learn about the brain from that. For example, you can stimulate certain areas, and then the patient who's undergoing surgery suddenly cannot speak, Okay, so you put an electrical pulse in it and the patient stops being able to produce language. And then we know, oh, that area, we shouldn't cut that area because we'll hurt the patient for life. But we also learn about the relationship between brain and language through that. And then, of course, functional neuroimaging, which has really been a revolution, fMRI, right? And, we can do fMRI, we can do voxel-based analysis and functional connectivity and all that stuff. And we know fMRI, right? Excellent. Okay. Some big questions in the field. Some big questions. So the first, I wrote just some of them where we don't have to answer them, but I think it's interesting to talk about them or maybe to think about them. The first question is about innateness and universality. This is kind of classically the nature versus nurture question, right? Is language, are we born knowing language or what do we know? Or do we learn it, right? Are we born blank slates? And it's increasingly interesting because there are so many different languages, right? We know in Hebrew, you have this weird root pattern, shoresh binyan thing that you have to know. But in English, we don't have that, right? And we know we have tonal languages where the tone of the word that you say it changes its meaning and so on. So there's a question, what's like the same about all languages, or what's the same in the brain, or what's different? I don't know, or maybe it's all different. If an alien comes to Earth, and studies humans, would it be like, okay, these are all different behaviors, or will it be like all the humans do something called language and they all have a little bit different manifestations of it, right? It's an interesting question. I think it's interesting. The evolution of language is a super interesting question. As I said, it's pretty distinctive in the animal kingdom, and we don't know how it evolved or what happened. Was it a sudden jump, or was there like a proto-language in between? When did it happen? 50,000 years ago, 200,000 years ago? There aren't really good answers to it. Language and thought is a super interesting question. Also in philosophy, what is the relationship between our thoughts and language? Do we think in language or not? Or do we think abstract independently of language? Some people report that when they think, they don't use inner speech, which is like talking to yourself in your head. And some people say they only think using inner speech. So it's an interesting question. Does the language affect how you think, right? Do the words affect your thoughts and so on? The specificity of the language faculty in the brain is actually a question that is it's very much researched. And the question is, when we talk about language in the brain, how specific is it just language? Like, are there areas which do only language, right? And are there pure linguistic abilities? Or is it related to other things like our ability to do math, or our ability to do social cognition, or, our working memory and so on, okay? So there are a lot of, you can put on the scale of language, it's a very, very unique and specific thing versus no, the brain does everything all at once, and language is just one manifestation, but it's related to all your other abilities and so on. Yeah, I think it's super interesting. And the last question, which I'll talk about, which is what I'll focus my talk about, is a question. It's considered the second biggest question in psychology after the nature versus nurture question. It's connectionism versus modularity. Okay, it's a big words, so we're going to explain them. Okay, connection versus modularity. I will say, yeah, there are two different ways to look at the brain in general, but we're going to focus on how they apply to language. Connectionism views the mind as interconnected processing units, right? We can think of it a little bit as like every faculty, every ability, every brain region is connected to every other brain region. It's a huge, big neural network, right? Not an artificial neural network, like a big neural network that influences each other from, and there are feed forward and feedback and all that stuff. And modularity thinks of the brain more as distinct and independent processing unit. We have one processing unit which does this, and then another processing unit which does this, and they can influence each other, right, or pass information from each other, but it's more divided, it's more compartmentalized. Those are little different modules, okay? If we do an analogy to computer science, connectionism really views the brain as like one big neural network, right? A complicated neural network with feedback and so on. You can think of it as a one big RNN or something like that. And modularity views the brain as like a script of many different functions, right? So you call, let's say, the letter recognition function, you recognize the letter, and then you call the letter combination function, and you combine the letters, and then you go access the semantics and so on, okay? So it's more of a script-like behavior. Some of the aspects are that connectionism believes in very, multi-domain interactionism. It believes that we use analogies and so on. And it's specific behaviors are distributed throughout the brain. There is no one region which does X and so on. And modularity is actually more domain specific for each module. It believes in rule-based, right? We apply rules to process the information, then we move on to the next rule. And it's more localized. It believes that there are certain brain areas which really do X, or it's more appropriate to say certain behaviors can be localized to certain parts of the brain and so on, okay? And an interesting thing is that the modularity, if the brain is modular, it will have a characteristic breakdown pattern. That means if one of the modules is destroyed, we will lose one ability, but we won't lose the others, right? And in connectionist framework, if something is destroyed, one brain area or whatever, we don't know what it will destroy. Like there's no easy mapping from functions to models, and there's no character breakdown pattern, okay? So that's an interesting thing. Now, I will say, I'm displaying these as two different opposing camps, and it's true, there are two different camps, and you can look at the history, which university belonged to that camp and which university belonged to that camp. For some reason, the East Coast University used to be more modular, and the West Coast used to be more connectionist, just a historical reason. But today, I think most researchers are somewhere in between. But I think saying somewhere in between is not enough. I think you should specify where exactly in between are you. Are you more modular? Are you more connectionist? And so on. And it can be different for different things. Okay? Excellent. So I'll give 3 examples of where this debate is relevant. Okay? So the first example is words and rules. Basically, when we produce a word or when we know a word, what do we know? Does our knowledge of words, does our vocabulary include a list of all the words? Or does it include a list of words and the rules of how to inflect them? Okay, so I'll give an example and I hope you'll all join me. This is a wog. Now there's another one. There are 2 of them. There are 2 wogs. How did you all know to say this word wogs? You never heard it before, I'm sure, right? But you all said it, right? So people take this to evidence that we have a plurality rule, which is add S in English, and we know how to apply it. So when we know words, we don't store the word, let's say, cat and cats as 2 different words. We store the word cat and dog and everything, and we store the add S rule or add ED rule, right? And this is a very modular way of thinking, right? You have the words and you have the rule you apply to the word. And you want to say cats, so you think of cat, and then you add the S, right? Something like that. However, the connectionist counterpart will be, no, it's just all a big neural network. We only know words, or we don't have a specific place where we know these rules, or these rules are not distinct from the words, and so on. And some evidence for it comes from a study where instead of wog, they use the word frink. So every Friday, Sam likes to frink. Last week, Sam frinked. Yeah, so some people say frank, like drink and drank. And it turns out that if you make the context that frank is more similar to drinking, more people will say frank, like drank. And if you make it frink more, the context is more like blinking, people will say frinked, like blinked. And that shows that we don't have this specific rule we apply, but we use analogies. It's kind of like prompt engineering. The context engineers our prompt how to complete this word and so on. But Pinker and Ullman are not, didn't stop there. They also showed that you can have 2 different types of patients. And then I forgot to say that obviously we have words in the language which are irregular. So for example, hold, you don't say holded, you say held. And these irregular words you have to keep in your head. You have to keep them as a separate list. There is no rule for them. So they show that some patients, specifically a patient with an aphasia in the frontal area, were still good at saying irregular words, but they were very, very bad at applying the rule. Okay? So that shows that something about the rule was destroyed. And a different type of patient was actually very good at applying the rule, but not so good at saying the irregular words. And even sometimes they would say the irregular words wrongly. So instead of hold, they'd say held. Instead of held, they'd say holded. Okay? And actually, we see that in children all the time. It's called overregularization, that children would say something like, I eated the purple berries instead of I ate. And we take this as evidence for the modular side, that when we learn these new words, when children learn these new words, they actually learn the words and the rules, and they're not very good at applying the rules. So sometimes they over-apply it. Okay? So this is kind of an example of a way of thinking. The connectionist side obviously has explanations for these phenomena. It's kind of a way of thinking between those two camps. Okay? I'll give another way where it's of the way of thinking between these two camps. So syntax and semantics. So the question is, what is the relationship between syntax, which is the structure of the sentence, and semantics? And more importantly, is syntax separate from semantics? Okay, so if you're thinking modular, you're like, we have the syntax and we have semantics, and those are two separate functions in the brain that we can call, right? And if you're thinking connectionist, you're like, no. We have language with the statistical rules and so on, and it looks to us as if syntax and semantics are different, but that's just the way we observe it. In the brain, it's all one big niche, okay? So Chomsky thought he proved that syntax is separate by saying the sentence, colorless green ideas sleep furiously. So this is a sentence which syntactically it's correct, but semantically it's meaningless. So it has syntax, it doesn't have semantics. And it turns out that people respond to this sentence in a weird way. They can process this sentence, some would say even easily. Like the syntax sounds right, even though it has no semantics. And this was taken as evidence that we process syntax kind of independently of the semantics from it, right? Interesting, no? But then there came sentences which proved otherwise. Those are called garden path sentences. And these are sentences, I don't want to read them out loud because it might ruin it. These are sentences, okay, I'm going to explain the first one. So the raft floated down the river sank. Is this a good sentence? No, it's not a good sentence. Actually, it is a good sentence. How? You say the raft, which was floated down the river, floated means someone made it float, sank. Okay? So actually, it is grammatically correct. The raft floated down the river, sank. But we don't process it as grammatically correct. Why? Because something about the semantics of it kind of lead you to process it in a different way than just how if you were only process the syntax. So this shows that semantics does influence syntactic processing. Okay? And you can try the rest of the garden path sentences, see if you can overcome your semantic bias and process these correctly. Okay? Another evidence to show that syntax is separate from semantics comes from patient studies. So the classic two aphasias that happen are Broca's aphasia. I'll play it, but I don't know if the speakers, you can hear them. So Broca's aphasia is a case where a patient understands what is being asked, can respond, but can't form sentences. It can't even inflect words grammatically. So,
What'd you do about it? Home, doctor, and legs. Walking, no good.
Okay, so I don't know if you heard, but essentially he answered the question, but he doesn't do syntax, but he does do semantics, right? There's no syntactic combination in there. And on the other hand, we have something that's called Wernicke's aphasia, where the opposite happens.
Hi, Byron. How are you?
I'm happy. Are you pretty? You look good.
What are you doing today?
We stayed with the water over here at the moment, talk with the people for them over there. They're diving for them at the moment. They'll save in the moment. He'll have water very soon for him. With luck, for him.
So we're on a cruise and we're about to
We
get to
will store it right here and they'll save their hands right there for them.
And what were we just doing with the iPad?
Right at the moment, they don't show a darn thing.
With the iPad that we were doing.
Right. So the patients with Wernicke's aphasia, they don't seem to respond semantically to the question, but they do produce speech, which is mostly grammatically correct. Okay, so you kind of see the distinction. And then we analyze the lesions of these brains, and Broca's aphasia tend to have lesions here in the frontal lobe area and the area that's called Broca's area or right next to it. And Wernicke patients have somewhere at the temporal parietal junction in an area that's called Wernicke's area. Right, so that's interesting evidence for the distinction between them. However, fMRI studies, for example, this study, which actually came out just last year, kind of tried to differentiate this thing. So it showed sentences which are grammatically incorrect, but semantically they could be meaningful, right? Like the boy throwing the ball instead of the boy is throwing the ball or something like that. And then showed sentences the other way, which are grammatically correct, but semantically meaningless, right? The boy is throwing, I don't know, the democracy or something that you can't throw, right? And then they want to see if there are different activations. And what they found, surprisingly, is it's very hard to find certain areas which activate more or differently for syntax as compared to semantics and vice versa. Okay, so they found here one area, but it's very small. It's not a very convincing finding. Okay, interesting. So maybe they are connected in the brain, and these patients, you can't study from patients. I will say another evidence, which is, I think, pretty well founded about the distinction, about this specificity of syntax, is the P600 ERP signal. So, you know, ERP, EEG, yeah.
Like creativity has effect on people's way of internalizing the sentence?
Yeah, so that's a great question. I have no idea. It's something creativity research probably should look into, and I don't read those articles that often, so I'm not sure. But yeah, it's super interesting and plausible. Anyway, the P600 component is an ERP component that is its amplitude is larger when you have a syntactic violation. Okay, but only when you have a syntactic violation. It occurs about 600 milliseconds after the violation occurs, and it shows something about syntactic processing, which is distinct from semantic processing, okay? So it's another way to think about modularity, connectionism in the brain, in syntax and semantics. And the third way is reading. Reading is super cool. It's super interesting. It's an ability which used to be that most humans didn't have, right? Very few humans have. But then we invented written language a few thousand years ago, and it really caught on. Every society that saw other societies that have a written language copied it, as far as I know. Like, societies really see that this technology is amazing, right? It's probably one of the most revolutionary technologies ever in the history of humankind. And now the question is, so in a modular way of reading, we would think of little modules. Like the first one would be a vision, look at the letters, right? And then the second one is character recognition, recognize the letters. And then the third one is combine the letters. And then the fourth one is maybe transform the letters into sounds that you know, so you can pronounce it, right? Or access semantics or so on. And we think of a very distinct hierarchical way of looking at it. And the connectionist view is, no, not at all. It's kind of an end-to-end neural network trained from the visual input to the semantics of the word or to the pronunciation of it or so on. Okay. So I'll give one evidence for the neural network view, and this is it. Can you guys read this? So how many of you read it wrong, the first sentence? Just one? Yeah? No, I'm assuming most of you. So what happened here? If we would look at the modular way of thinking, then we would have read, do, love, you, me, right? We would combine these. But something in the brain, I don't know, switched it up to make it look, do you love me, which makes a lot more sense, right? So this shows a top-down interference, interactionist, connectionist view, right? You read that wrong. Another evidence is this kind of text. Can any of you read this? Yeah, you can. So usually you got to kind of prompt it and you start, isn't it amazing that you can? And then people suddenly can read it. And it's crazy, right? but somehow what you know about the words and what they should look like helps you read things even when the letters are incorrect. So this is strong evidence for the connectionist view, right? You agree with me, right? And a third evidence is that according to research at Cambridge University, it doesn't matter in what order the letters in a word are, as long as the two outmost letters are in the correct place, the middle letters can be jumbled up and we still read them almost seamlessly. So that's pretty crazy. However, okay, so we said this is the connectionist view. That's all kind of like one big network. However, there is evidence for the modular view. You see that goes step by step by step. One of the evidence is that there are dyslexia. There are two kinds of dyslexias, actually. There's a dyslexia where you can't pronounce words. You can't convert from letters to their sounds. But if you already know this word, right, you recognize it, like you've read it before, you can read it. So you can only read words that you know before. You can't read any new words. And there's a different dyslexia, which is the opposite. You can't remember or keep in memory holistic word reading, where you read the whole word, but you can convert every letter to its sound and read that way. So words which are written irregularly, for example, listen, which has a T in it, these people will read it listen. No matter how much you try to teach them, they will always read it in the orthographically regular way. And there's also evidence for in the brain, there is an area which is suspected to be the visual word form area. It's on the left fusiform gyrus, which apparently it responds to words and not to jumbled up letters. But it doesn't care what font the word is, what size the word is, right? If it's capital letters or not capital letters. And yeah, so it's pretty interesting. So there is support this way and this way. Again, open question. Okay. Excellent. So we're going to move on to part 2, which is data science and NLP tools in neuroscience of language, right? More applicable for this course. Before I'll talk about NLP tools, I just want to say language and language behavior that we collect in the lab, right, is a signal. It's data like any other data. So you can always do data science stuff on it, right? You don't have to do NLP stuff on it, okay? Every signal that you take, you take your signal processing course, your machine learning course, your whatever data science course, and you can apply it. So I'm just giving an example of 2 cool studies where they just did pure data science that happened to be on linguistic behavior, which is cool and interesting, okay? And then we'll go on to the NLP part. So what happens is they let people read text on screen, and they looked at the eye pattern behavior of reading text, right? So you have a characteristic saccadic behavior where we fixate on a word and then we skip to the next word. Sometimes we skip over words, sometimes we go back and so on. And then they asked an interesting question. Let's take speakers who speak some first language and have them read in English, which is their second language. Can we see how from their eye movements in English, what their first language was? You understand the question? Does your first language affect how you read in the second language in English? And they did. They succeeded very well in predicting. The language they had here were Portuguese, Spanish, Mandarin Chinese, and Japanese, I think. Yeah, so they could do it. And then they also wanted to ask, same thing from the same eye movements is, can we use these eye movements in your second language in English to predict or to tell how good you are, how proficient you are in English, right? So just from looking at your eye movements when you're reading, I can tell, or the model can tell, much smarter than me, the models obviously, how good you are in English. And they did. They found a correlation that's very good from their predictions and the actual proficiency. That's pretty good, no? So yeah, and these, and also saying that these data sets were released to the public and many other data sets. So if you ever have an idea of a data science project, or you want to, I don't know, try out a new model that you thought or whatever, and you're thinking of data that you want to use, you can always use linguistic data, right? It's interesting, right? It's very versatile. But the focus of the talk is actually about NLP and neuroscience. So now we're going to say how these two fields combined, okay? I will say, I didn't say this earlier, there were two big problems in neuroscience of language, technical problems, not questions, that NLP helped us solve. And today our research is better because of it. So I'll describe the problems and then you'll tell me how you think NLP helped us solve. The first problem is word predictability. It's a fundamental agreed upon assumption. There's a huge consensus that words which are more predictable are easier to process. What do I mean? That, for example, if I look at the word bridge, when I say the boat passed under the bridge, it's easier to process this word than if I would say the artist was painting the bridge. Because here it's more predictable, right? And this, I know I can see in your heads now, you're relating it to predictive processing in the brain and active inference and all that good stuff that you know. The problem is, how do we measure how predictable a given word is in a given sentence, right? I give my subject, my participants in the study sentences, and I say, okay, the bridge here, it feels more predictable than here. But how do I apply numbers to this, right? You understand the problem? And we want to do it even for sentences which have never been said before, right? Because you can say, okay, let's look at the boat passed under. We'll look at the entire books, all the internet, whatever, and we'll see how many times bridge follows that sentence or so on. The problem is for most sentences, if a sentence is over 10 words longer, it's probably never been said before. Like it's most likely that you will search the whole internet and you won't find it, right? But you still want to estimate these predictabilities. I'll just give an analogy. No, I'm not going to give an analogy. Instead, I will say what we used to do is to ask a lot of people. We used to take 100 people. We would say the boat passed under the, and ask them what word goes in there. And then we see, oh, 70 people said bridge. That means that bridge is 70% predictable and so on, right? But that's very problematic. First of all, your resolution of your probabilities is bound by your sample size. You need to ask hundreds of people to get a good, accurate probability. It really underestimates low predictability word, because if there's a word which its predictability is, let's say, 1 in 10,000, then you need to ask at least 10,000 people to get even one response. And it's very time consuming and expensive. Even with Mechanical Turk and all these online good stuff, this can take, months to collect all this data. All right, so what's the solution? How do we solve this? Yes. Right, but that would compare a word. So I would do how bridge is similar to what? To the or to under?
Building power for other things, or versus like democracy. Maybe building.
Yeah, but I understand. But the problem is, like, I want to see how predictable it is given the entire sentence which preceded before. And the sentence which preceded before, it can be very long. It can be 10 words, 15 words, 20 words, right? So the similarity is not in. What can I do? Yes? What embedding? The vector embedding?
Sounds more frequent for that.
Right, so the embedding, this vector only tells us relations between words, right? So how similar two words are. But I want to see how predictable a given word is given a sentence that comes before it. So it's not enough, yeah? But what words? It's a word in a sentence. Again, you guys are and the sentence has never occurred before, right? I'm going to invent a new sentence. I'm going to make it 10 words long. You've never heard before, and I want to have a predictability score. Yeah. Yeah, so that's what people used to do, but it's not good enough. The probabilities are not good enough because you want to estimate the probability of bridge given the whole 5 words beforehand, and then estimating probability given 5 words, it's more difficult. Okay, the answer is actually the other thing of NLP is the language models. What did we say language models do? You give them a chunk of a sentence, and then they give you the probability for every word to follow. Right? Remember this? So this is much, much easier. This is what we do today. We put in the first part of the sentence to GPT, right? Or whatever large language model that we think is good enough. And then we look, what is the probability for every word that we want that the language model outputs? So simple. It takes me 5 minutes in code in a computer. Yes.
The distribution of the probability is the same as the human process.
Right, and that is exactly the assumption that we make. It's not clear, but the paper Smith and Levy 2011 explicitly wrote this. It wrote a trade-off of assumption. Do we assume that these models track probabilities in a similar way to the human mind, or do we assume that the collective, 1,000 people response is actually more reflective, and then we have to do a trade-off. It turns out that what people did is said, let's make this assumption and see if it works in the real world. Like, see if it works on data. And that's exactly what happened. So for example, Smith and Levy from 2013, they estimated probabilities using the language models of 2013. This is pre-transformers. This was actually an RNN, an old machine learning, from the before times. And they measured it on the self-paced reading times and on the fixation duration for every word. And they saw an amazing, it's actually a logarithmic relationship because the x-axis here is a log scale, okay? But the more, the less predictable a word is using these estimates from language models, the more time it takes to read it or the longer the eye will fixate on it, which is pretty amazing. There have also been brain areas which have been found to correlate with the predictability of a word. So you give people a podcast to listen to, and you do the predictability of the word at each given word for the podcast, and then you see what brain activity correlates with the predictability of these words. And this is a finding, my finding, it's unpublished actually, that we can also, so on the x-axis we see how surprising a word is, which is actually like how improbable it is. It's just a log transform of the improbability. And the colors mean the longer time of the duration for the eye fixation to stay on the word. So we looked, as we move from words which are more predictable to more surprising, then it also takes longer duration in milliseconds to fixate on them. But this is only true at the bottom half of this graph. And the bottom half is how constraining are the sentences. So when a sentence, the boat passed under the, is pretty constraining. There aren't a lot of options there. So there we would see a big difference between bridge and, democracy or something that's very surprising. But if we have open questions like, yesterday I went and, it's an open sentence. The context is open. So we don't really observe that difference between things which are predictable and not predictable within that time. Okay, so it's pretty cool that predictability interacts with the constraint of the context. Okay, the second problem, how we're in time. Oh, we're great on time. The second problem is the problem of word representation and semantic similarity. We want to represent the semantic content of the word, okay? It's very easy to represent physical features of the word. For example, the word dog is 3 letters long. It's very easy to say, okay, the length of the word, we just count the letters. But how do we represent the meaning of the word dog? And what's important is that all of our statistics and all of our machine learning, as you know, they have to get numbers as input. Could be numbers, could be vectors, matrices, whatever, but it has to be numbers, the language of math, right? So how do we take dog and convert it into a number, which captures its semantic content? And then we could use the words in our mathematical and statistical models and do statistics on them. And we want to measure also the semantic similarity between words. I'll just give an example why it's useful to represent stimuli using numbers and related stimuli get closer number values from vision. So in vision, we can present 2 Gabor patches, right? And see the difference in brain activity or whatever between the Gabor patches. And it's very easy to quantify 2 patches, how similar they are to each other, right? We look at the orientation, we look at the brightness, we look at the contrast between them. We get a few 5 or 6 numbers or so on, and we can see when the Gabor patches are similar, and then we would expect the brain activity to be more similar, and when they're different, and we would expect brain activity to be more different, right? But for cat and dog, how do we do that? What were we measuring here? What's the answer? Word embedding. So this is where word embedding came from. And essentially, we take the pre-trained word embeddings, which are these vectors. Usually today, the good ones are only about 300 numbers long, right? It's not a very large vector. Some are over 1,000, some are like short in 100 and something, and so on. But that's enough for us to, let's say, we can give participants, let them listen to a podcast, and then at every given word, we will take the word embedding, this 300 long vector, and try to see what brain areas respond. And the brain areas that respond in accordance with the word embedding, we say these are brain areas which are involved in the semantic processing, because we assume that this word embedding captures something about the semantics of the word. Okay? Yeah, Itamar?
Every model has things embedding.
Right, but that's why you will get, when you put in the different embeddings, you will get different weights to map it to the brain activity. But what we assume is that all these embeddings are good enough so that the semantic similarity is captured in all of them. So a brain area which is activated according to the semantic content, we can predict it or, correlate with it using any different embedding that we need. Like all of them have the semantic information in them somehow. We will just have to use a different model to connect them to the brain activity. And that's exactly what Alexander Huth did. In an amazing study, he played a podcast for participants, and then he put in the word embeddings, and then he wanted to see which brain activities respond in accordance with the word embeddings. Or I think a more accurate way to say it is, which voxels can we predict the brain activity during the podcast using the word embedding? So we kind of hone in on the semantic information from the word embedding and use it to predict the brain activity, okay? He used simple linear regression to predict the brain activity from the word embedding, okay? And then he compared, of course, the predictions with the actual bold responses per voxel. And what he saw, he claimed that the entire brain is related to semantic processing. There's no one area in the brain which is semantic processing. But if you actually look at the maps, I think it's actually clear that some areas here are not involved at all. And many areas, parietal lobe, temporal lobe, and so on, are more involved, which actually fits previous theories, where semantic processing is done mostly in the temporal and parietal lobe. Okay. And then he also did PCA to see different types of words, how they activate different types of areas. Okay, and if you want to explore that further, you can go to this link and you can input any word that you want, and it will tell you which brain areas his model predicts will activate for a given word. Right, so that's pretty cool. I recommend putting in your own name and seeing which brain areas does this model predict will activate when you put in your own name. Okay? But Alexander Huth didn't have enough. Later, this was in 2016, took him 7 years later in 2023, he said, let's do the opposite way. Now we will go and look in the brain, in the voxels, and from the brain activity, we will try to predict what word embedding was just heard. Okay, so this is the difference between encoding and decoding in neuroscience, right? And he succeeded to a scary amount. Like, this is literally mind reading. Essentially, he builds a model that takes in an input, the brain activity from all the brain voxels, and then from the entire, all these voxels, we do a complicated, it was actually a linear regression model, so it's not very complicated, but a model to predict which word embedding was heard at that time. And then they went to their, they converted the word embedding to the actual word, or to the word that was nearest to it that they had in the dictionary. And as you can see here, the comparison between the actual stimulus, which was heard in the decoded stimulus, is very, very good. It's very close. So just from reading your brain activity, we can, to some degree, know what words you were listening to at the time. Pretty cool, no? pretty crazy. There are ethical implications to this study. Right, these are just more showing brain areas which were more helpful in predicting and brain areas which were less helpful in predicting, and so on. It turns out, I will mention this because this was a finding that they mentioned in the paper. I thought it's very interesting, that it's much easier to predict words which are concrete versus words which are abstract. There's something about the information in the brain that represents concrete words in a way that's easier to decode that information than abstract words. And this is something interesting to think about, I think. I thought it was super interesting myself, yeah. So you can listen to Alexander Huth talk about these two studies on this episode of the Language Neuroscience podcast. I really recommend it. You don't need any expertise. You don't need any previous knowledge. And he's a very fun guy. He talks very simply, explained what he did, he explained what his findings are. And he even released some of the data in the code if you want to train a model yourself to better predict the words than him, to beat him, you're more than welcome to. I think it's very difficult, but I think you guys can do it. Okay? Awesome. And now, just so we understand it, why not both? Why not use both? And I think this study will hone in on the two ways which language models helped us measure predictability, and word embeddings helped us predict similarity. And here's the research question. The question is, what is the effect of semantic similarity between a word which is highly predictable to come in a certain context and the actual word which appeared? So here's what I did. I gave a sentence, a dog is a man's best companion. Okay, so it's not very predictable, companion, because friend is very, very predictable in this context. Okay, however, companion and friend are semantically close. Okay, and if I would have given a different example, a dog is a man's best, I don't know, tool or something, tool and friend are not very close, right? So we're going to ask, what is the effect of the semantic similarity between the actual word and a highly predictable word which was supposed to appear there, right? And if we think that the brain is actively predicting the highly predictable word, so what is the effect of semantic similarity? And what this study, very interesting study, showed that this is on, again, fixation duration, so how long the eye rests on this word. It showed that, this is fixation duration, and this is total reading time. And this is the first fixation duration, this is the gaze duration, this is total reading time. Let's focus on total reading time, is that the more similar these words are, the word which actually appeared and the word which was predicted to appear, the less reading time it took for this word. So companion, even though it's surprising here, it's not predictable, because it's similar to friend, it actually takes lesser time to appear than a word which would be dissimilar. And if you understood this study, then you're experts on the intersection of NLP and neuroscience of language, because it uses both the predictability and the word embeddings. Cool, huh? Okay, I'm going to move on to part 3. Yeah, I'm going to move on to part 3. I will say part 3 is more speculative. It's a little bit me sharing my thoughts with you, but it's really, really okay for you to have different thoughts, and I'd love for you to share them as well. We are in the middle of a kind of a revolution because of the success of large language models. So ChatGPT came in, 2021? Beforehand, GPT-3 came in, let's say, 2019, 2020. And they're really successful. It really looks like they know how to do language, these AI models. And this was surprising. We didn't think that just a huge transformer neural network trained on the old internet would be able to do language. And there's a question, and I think this is a core question now, is what can we learn about the brain from these models, right? Like, what can we learn about the brain from the success of these models? I'm not saying we know how to use these models as tools to measure predictability instead of doing these long questionnaires. Okay, obviously we can use them as tools, right? The question is, are they a scientific model of the brain? Okay, is that understood? Is that clear what I'm getting at? And I think there's a similar thing happening outside language with vision, right? We have these amazing neural networks which can detect any image, right? They can detect what's in the image. How similar is that to human vision, or not similar, or is it? And I think today with other amazing models, we compare them in other regions. But I think language, for some reason, is where the debate is really fierce. Like there's a very strong debate. There are people with very strong opinions on other side. I don't know if that's the same in other places. So just to exemplify, we have this huge success, and we have a kind of a debate where some people say, could a large language model be conscious, right? They ascribe it consciousness and agency and so on. This David Chalmers, he's a philosopher, so he's not a neuroscientist. And then some people say, oh, no, these are just stochastic parrots, random parrots. They have no idea what they're doing, nothing. And you have these arguments, and Sam Altman says, Sam Altman is the head of OpenAI, and he says gradient descent can do it. Gradient descent can be enough for a model to be fully intelligent, just like a human, and so on. And some people say, no, it's just a computer that talks, and so on, whatever. But the question we are going to be focusing is what can be learned from LLMs about the neuroscience of language. And here there are two camps. The first camp is Noam Chomsky camp. This is an actual Noam Chomsky quote that he gave from a podcast, I think it was 3 years ago. Noam Chomsky, I don't know if you know, he's the head of modern linguistics. He's probably one of the most influential people of the last 100 years. And this is his quote. We can ask the question, is it useful? Yeah, it's pretty useful. I use Google Translate, right? These models are useful. So on engineering grounds, it's kind of having like a bulldozer. Does it tell you anything about human language? Zero, nothing. Okay, so this is a very extreme point of view that's saying large language model don't tell us anything about human language. They're just cool engineering things. On the other hand, we have researchers, they're mostly young researchers like Piantadosi, who say the exact opposite. He published a paper, modern language models refute Chomsky's approach to language. They're like, no. Everything Chomsky said in all that approach is just wrong, right? And large language models are the model to the brain and so on. It's pretty crazy. I think today, most researchers are somewhere in between, but it really depends from faculty to faculty and from researcher to researcher. I'll give you a little bit inside scoop. Here in Bar-Ilan, we're pretty much in the middle. I think maybe today more lean towards the Piantadosi side, but on Tel Aviv University, I think they more lean towards the Chomsky side and so on. So it just happens. That's how it happens in science. We'll see who's correct at the end. But right now, no one knows. I will say, if you really care about this question, I can't recommend enough a podcast called Machine Learning Street Talk. They've been documenting experts on the field on exactly these questions for the past 5 or 6 years. They have amazing interviews. They also have videos, if you like YouTube videos. They also do other stuff about machine learning, which is not related to this, but they're really good about this specific question. And there's also a blog post which explains why Chomsky thinks the way it does and why some people disagree, which if anyone wants to read. I will say, okay, and I will give one kind of modern study, which is more to this new side of LLMs. We can use them to learn about the brain. So in this study from Ariel Goldstein that was published in Nature, they used GPT-2 and recording from the human brain, but they used patients, so they had good data, because patients you can put in electrodes in the brain. It's not just EEG. And then they wanted to see if they, I didn't have the findings, yeah. Okay, so we'll go over the results. They wanted to see if they can predict brain activity from the word embedding, or the contextualized word embedding, even before the word occurs and after the word occurs. I don't think we'll go into it. It's a little bit late, but we can read the paper. But essentially what they show here is that you can predict the brain activity even almost up to a second before the word occurs, and of course after the word occurs, from GPT-2's representation of the word in context alone. And you can also predict, and it works better for words which are predictable versus words which are surprising. If a word is surprising, you can't predict it beforehand as good as afterwards, which makes sense with what we know of how the brain works. And they also showed that if you use just the word embedding, like the way Alexander Huth did it, where you use just word embeddings, it's not as good as using GPT-2's embedding, because GPT-2, its embedding takes into account all the sentences beforehand of the word. So for word embedding, as we said, is a way to map a word to a vector. GPT, these large language models, they map the whole input into a vector, and then from that vector, they give the probability for the next word. So mapping in the whole sentence which occurred previously allowed us to predict the brain activity better than just using the word embeddings. But what I would like to focus on is the language that they used in this study, because I think that's more interesting for a question. So I'm going to read it. Our findings suggest that GPT-2 or LLMs provide a new and biologically feasible computational framework for studying the neural basis of language. Okay, so look at how strong of a statement that is. And how are they similar, or what can you learn about them? There are three computational principles. One, both are engaged in continuous next word prediction before the word onset. So we can predict brain activity for a specific word even before it occurred, just like GPT-2 is trained to predict the next word before it occurs. Both match their pre-onset predictions to the incoming word to calculate post-onset surprise. So after you see the actual word which occurred, if it's what you predicted, that's good, no loss, we're good. If it's not the one you predicted, you have a loss signal, and you have to backpropagate and update and so on. And both rely on contextual embeddings to represent words in natural context. So we don't only process each word individually, but we kind of look at the whole sentence. I think that's interesting that we use GPT to learn about these things about the brain. Although some people would say, we knew all these things without LLMs. The LLMs didn't really help us here. You did a cool study, it's cool, but we could have known that even without LLMs. That's a question, so I don't know. I'll end, this is my last slide, one before last actually. I'll end here with 4 common arguments, 2 for the idea that large language models are models of the brain or can be used or whatever, and 2 against. Okay, so I did green and red. Okay, but I would love to hear if you have any more arguments here or there and so on. What are your thoughts or about these particular arguments, if they're good or not good, so on, okay? Excellent. So the first argument for is that these models correlate with brain activity significantly better than chance. And no matter how you slice it, there's some information in the models which correlates with information in the way how the brain predicts. In this study, they actually took a model which had, it's a deep neural network model with 50 hidden layers, deep layers. You know that the neural networks have deep layers. And they actually saw that each individual layer correlates significantly with brain activity, sometimes with other areas or with other times. But it's not only that, I don't know, the last layer or one representation of the model correlates with the brain, but actually each individual layer, every step of the way in the large language model correlates with brain activity. And that's very difficult to explain if you assume that LLMs do one thing and human brains do different thing. LLMs do language in one way and human brains do language in a different way. How do you explain these correlations? It's very difficult, I think. I went and asked one of the people who's very much on Chomsky's side, published a refutation to Piantadosi and so on. How do you explain these brain correlations? What is your explanation? And he said that he thinks that these brain correlations have nothing to do with the actual language or language representation or syntax or so the things we call language, but only has to do with next word prediction. Surprise. So this is all about a large part of the brain is devoted only to predicting what the next stimulus will be. Happens to be that when we hear language, we're predicting what the next word will be, but it's not a core language part of the brain, or not a core part of the language faculty. And that's where the correlations come from. I don't know if I buy it or not. It's up to you to think about it. Okay. One argument against the use of LLMs, I'm sure you've thought of this argument, is the acquisition. Okay, so LLMs were trained on the whole internet and Wikipedia and GitHub and whatever. That's very different than human babies, right? But human babies are not trained on the whole internet at all, right? And we know that the training data is vastly, vastly different. Also, LLMs use a technique called backpropagation, gradient descent, backpropagation, that thing. And there are very numerous studies that show that backpropagation can't happen in a biological brain, at least not in the gradient descent way that we classically know. Okay? So yeah, so you say they acquired completely differently. There's no similarity here at all. So obviously they can't be comparable. Obviously they learn like in a different way. I will share with you that I don't think it's such a good argument, and I'll tell you why. Very often we use mouse models. For example, we have a mouse model for Alzheimer's, but the mouse didn't get Alzheimer's the same way humans get Alzheimer's, and we still use it as a mouse model, right? So if you take this argument seriously, I think you would have to be against mouse models as well for most things. And I think that's very drastic. But that's my opinion. Maybe the Alzheimer's in the mouse model, is similar. We engineer it to be similar to the human brain in the way that we don't engineer these LLMs to be similar to the human brain at all. So yeah, so it's something to think about. Okay. Another argument in favor of using LLMs, and this is a good argument. It's been implied, I implied that the people who support the use of LLMs as scientific models, they tend to be on the connectionist side. They're not modular. Because LLMs are very connectionist. They don't have syntax and semantics built in separately. They don't have words and rules built in separately. Right? Actually, if you think, they have a different representation for cat and cats. Really. And so on. And yeah, so it's very much a connectionist point of view. Okay? This makes sense, by the way, because Chomsky was really from the modularity perspective. The big people supporting modularity afterwards were actually Chomsky's students. It just happened to be. And a big argument, I think, in favor of LLMs as models or of the connectionist view is that every single thing that the modularists said that a large neural network cannot do, that's impossible to do without rules, LLMs done it. Okay, so we have 50 years of people from the modular side said that you can't process a sentence like colorless green ideas sleep furiously if you don't have a separate syntactic parser and semantic parser built into the model. If you just train your large model on language, it will never be able to process this sentence, right? And so on. And just to make sure it's true, so I gave it here an experiment that I did, a one-time experiment, and I gave a sentence. I gave two sentences. I don't know if you can see. There's a zoom. I gave two sentences. Sleepless master students correlate recursively, or recursively correlate students master sleepless. Which one is what? Which one didn't sound good? The second one is meaningless, right? I broke the syntax. The first one is also meaningless, but it's syntactically accurate. And this is exactly the colorless green idea sentence. Just ask ChatGPT which sentence is grammatical in English and which isn't. Now, I'm telling you, 50 years of people saying no LLM can do this without separate syntactic parser that's modular and a separate part of it, right? No large language model can do it. Obviously, none of these sentences were ever in the training data. I checked, I look up on the website, nobody ever wrote. I look on the internet, on Google, nobody ever wrote these sentences and so on. And first answer, no edit, no retry, no prompt engineering, no anything. ChatGPT answered that the first sentence is grammatical and the second sentence is not grammatical. This was a huge surprise to people, and some big support for connectionism. Now, I will say, ever since ChatGPT did all these impossible things to do, people who support the modular view came up with new things which are impossible for it to do. Yeah, so today, if you look up, there's still probably between 10 to 20 things which are kind of known that it still can't do and humans can do. And that's why it's not like humans. No, I don't think it's a good argument. You said that before. Yeah, so that's what I think. However, the last good argument which I will employ against the idea of using LLMs as models for the human brain is the problem of multiple realizability. These are big words. We're going to explain them. multiple realizability is an idea from philosophy that two algorithms or behaviors or states that we observe or so on can be implemented by two completely different ways or so on. One example that people give is that phenotype identity is not genotype identity. What does it mean? Phenotype is the way we perceive, like the way the genes have been expressed in something we can see, like hair color is a phenotype. But just because two people have the exact same hair color doesn't mean they have the same genes. They could be two different genes which both code for the same hair color. I'm sorry if the hair color example is not true. I don't know genetics that well, but I know for a fact that you can have two different genes or two different alleles of the same gene, which would code for the same phenotype. So just because we observe the same phenotype doesn't mean that the gene, the allele is the same, right? And I think Mars level of computational analysis is a good framework to think about it. Any problem can have a computation, like anything we see is what problem is it trying to solve, right? So here the example is the problem of flight. We're trying to fly, but it can have two different algorithms to fly. Algorithm here, Mark just meant different rules, right? Different ways it can fly. So birds fly by flapping their wings, but quadcopters fly by rotating their rotors, right? And obviously, implementation in the physical world can be different. Birds, biological, they have DNA and cells and so on, and quadcopters are made of plastic and electronics and so on. So just because we see something that flies, right? So we see, a quadcopter flies, doesn't mean we can use it to learn about how birds fly. Maybe we can, maybe we can't, but it's not necessarily so. Yeah, I will say, I gave this talk, I don't remember if it was last year or 2 years ago, and I had someone who studied physics at the audience, and he said, of course we can. We can learn a lot about how birds fly from how quadcopters fly. So I don't know if it's true like in physics world, but I do think the way quadcopters fly, at least on the implementation level, is sufficiently different from birds that people who study birds, ornithologists, don't go and look at quadcopters. Like they don't use them as models. So that would be my response. Okay, I'll end this talk with some food for thought. Historically, every time the brain was compared to the best technology at the time. This is all true. They thought brain was like a hydraulic machine. Brain is like a clock. Right? Oh, it's like a clock. All the little gears work together, right? Brain is like a steam engine. Brain is like a telephone switchboard. Brain is like an electrical circuit. Brain is like a computer, right? They invent computers. Then they invent the internet. Brain is like the World Wide Web. It's all interconnected, And today brain is like a GPT, a generative pre-trained transformer, right? We're here, right? So I don't know if that says something. However, maybe this time it's different. Maybe, we've actually hit on something this time. So that's some food for thought. And thank you very much. Thank you for listening. Be happy to take questions.